goal of this project is to design a device that has the capability to receive and display radio frequency signals in the range of 80 MHz to 3 GHz. This project is sponsored by Phase 1 Engineering and is a combination of an art piece, functional lab equipment, and a design showcase. This project boils down to a piece of hardware along with software to control and communicate with all designed devices. It's important to understand a few definitions before diving into the project. So, what is RF? Well, wireless communication is made possible by creating and manipulating electromagnetic waves. Think of things like cell phones, Bluetooth, and Wi-Fi. Without diving too deep into the physics, these waves are able to travel through a vacuum, or air, and arrive at a desired destination. Because these waves are all traveling through the air at any given moment, the continuous RF spectrum can get busy. A good analogy would be a room full of people all trying to talk at once. For this reason, governing bodies around the world spend a great deal of time allocating radio spectra for people to use, like this frequency allocation chart from the US government. These allocated areas are often called bands, like the FM radio band or the 2.4 GHz Wi-Fi band. For companies like Phase 1 Engineering, who work with sensitive RF devices, it is very important to understand exactly how busy a given band is. The reasons are endless, but the goal is the same. A device that could see and show this information to the user is very helpful. This type of device is known as a spectrum analyzer. Our spectrum analyzer consists of 3 essential elements for completion: RF design, embedded programming, and mechanical design. Let's tackle each of these one by one. Our RF design approach uses a combination of common radio designs to achieve our desired operational range. The final design is a combination of a super heterodyne radio that uses a second mixing stage for in-phase and quadrature digital signal processing to reject unwanted image frequencies. Once the signals are received by the radio front end, we pass them off to the radio back end, which converts the signals into a readable format for the control software. Our radio front end consists of the following: an antenna multiplexer, a low noise amplifier, a user adjustable attenuator, another low noise amplifier, the first mixing stage, the second mixing stage, a final cascaded amplifier stage, and a final filtering stage. The electrical design choices are inseparable from the RF design choices of the project. This project makes use of 9 custom PCBs that all require unique considerations from an electrical design standpoint. RF devices are highly sensitive to noise and interference, so a great deal of care was taken to isolate the RF and digital electronic chains. Our power distribution consists of a 5 and 12 volt AC to DC power supply, along with a custom power board that conditions and distributes voltages across our system. The embedded programming consists of an FPGA implementation on a Spartan 7 chip along with a Python program that runs continuously on a Raspberry Pi 5. The FPGA is used to take in parallel inputs from 2 ADCs at 35 to 65 MHz and calculate a fast Fourier transform to decode the frequency content of the signals. The Pi 5 controls every piece of hardware in the system. From the Pi 5, we communicate with the antenna multiplexer, the input attenuator, and the output IF filters. All this communication is done with simple output GPIO pins. For more complex information, we make use of a SPI transmission bus. The SPI bus contains both local oscillators for mixing and the FPGA device. The user interacts with a GUI created in Python that runs on the desktop of a Linux environment. The mechanical design portion of the project involves many aesthetic and practical considerations. The enclosure of the device is an aluminum alloy box with a plexiglass front panel to view the electronics. We chose to design our spectrum analyzer as a sliding rack system. This is a practical choice that allows us to mount the bulk of our electronics onto a conveniently removable rack. The front I/O shield has 4 N-type connectors for RF inputs and peripheral inputs for the Pi 5, along with power to the system. The opposite end of the I/O shield contains 4 fans for cooling the system during operation. Many of the major obstacles of the project have come from getting the spectrum analyzer to operate as one cohesive device. We were able to very quickly get each block in our block diagram to work properly. However, as with most RF designs, the trouble comes when plugging everything in together. Problems with noise, aliasing, and self-interference have caused many issues throughout the development process. Speed has also been a difficult obstacle to deal with. For the most part, our system is bottlenecked by the communication speed from the Pi 5 to the FPGA. We originally thought our SPI communication speeds would reach upwards of 20 MHz. In the end, our practical limitation is somewhere closer to 5 MHz without packet degradation. That being said, we were able to get the device to operate in the entire range of interest with some limitations on refresh rate. Here we will demonstrate an example measurement of the Wi-Fi and Bluetooth band. The program is launched by opening the terminal in the Linux desktop. The program starts in showcase mode. We can enter the mode to change the desired measurement range. Here we will choose 2440 MHz to 2455 MHz as an example. We can see that the signals dancing on the screen jump out of the noise floor. These signals correspond to any device that may be communicating near 2.45 GHz. Common devices are Wi-Fi routers and Bluetooth headphones. We hope you enjoyed getting to know more about our project. Thank you to Phase 1 Engineering for allowing us to complete this project. Without their help and support, this project would not exist. Thanks for watching!